Hello everyone. My apologies. Thank you, Gabriel. Let me begin again, and welcome to PCTE's webinar for 2017. This is our last webinar, and it's going to be a bit of a summary of the training content from the previous year. I'm also going to talk a little bit about the new products and a few new things coming early in 2018 as well. So let's jump in, and sorry for the audio. So the 250 Alive Array is the next system launching and available from ProSec. This takes the same concept as the ProSec GPR Live, where they make the NDT system to an Apple iPad. In particular, this is going to bring all the same B-scan imaging, C-scan and 3D imaging you can get with the ultrasonic pulse echo array, the best tool for identifying voiding and damaging concrete. We'll actually talk a little bit later about this when I discuss the content from our training webinar with seminar with ProSec we completed. But specifically, this system is also going to bring it all onto an iPad-based application, allowing remote reporting and cloud-based sharing of the data, and full and powerful processing inside that application. We're really looking forward to this one. We've been amazed with how much you can do with the ProSec GPR Live. We think this is going to be just as good. For the laboratory range next year, we are always improving our laboratory stock, bringing in new large-scale testing equipment and consumable accessories. In particular, we're intending to have a new mark of cylinder molds available with a locking lid. And something important to us has always been having the right sensors for quick application where you need to get something out on site quickly. So we're now stocking, in addition to the strain gauges we carry from Geosense, our geophysical and structural sensor provider, we are now keeping in stock their data logging systems and their VW crack meter displacement systems. These are excellent if you have a long-term monitoring requirement for a join or a crack where access is hard. You can place the VW sensor out on the soffit under a bridge where you would need access equipment to get to, and run quite a long cable run. You can easily go hundreds of meters with vibrating wire sensor cables into the data logger and collect the data from a much more convenient access point. And something I'm really excited for is the continuing improvement of the camera controller. If you're not familiar with the camera system, this is a data logging system by Protector, specifically used for corrosion information. They have a number of nodes which are placed close to the sensors, allowing very short cable runs to sensitive electrochemical measurements, and then a digital bus carries power and signal back to the central controller. In addition to the conventional half-cell potential measurements and LPR measurements available on the system, they've introduced a number of new nodes, which we'll be updating our website to explain shortly. But as a quick summary, they now have nodes suitable for measuring potentiometric displacement sensors. So this is another way to get displacement and motion on a structure close by. They've also introduced a new microcontroller node, which is a great way to log small values of half-cell out on a limited application. Rather than needing the whole system to be deployed, the microcontroller node can monitor a couple of reference electrodes in the critical areas. There's also improvements in their humidity node, which is suitable for measuring in situ or ambient humidity. And a new P plus T node, which measures half-cell potential and a T-type temperature sensor. So if you want to confirm the change in potential due to temperature in your structure, this can be a very useful way to set that up and have it all go into your central data logging system. So look, that's the quick summary of what's new hardware-wise. We'll be updating throughout the year as we go, but I really wanted to catch what was new before we finish up. So let's begin our training content. I'm going to start by offering the most useful section, I think, from our ProSec training seminar, which highlights the difference between several concrete imaging techniques, so it helps the operator choose the best tool for the job. I'm also going to give a bit of a preview of our first webinar in 2018, which is going to be on coating inspection equipment. So that's dry film thickness gauges, pull-off testing and similar. In particular, the preview is going to cover testing of galvanizing. That's always a big question, and I want to get the word out as soon as I can. I'm then going to go over a little snippet from the 2 previous webinars we've done this year, review of the non-destructive tests inside AS 5100.8 and the early age strength review. So, we completed our training seminar with ProSec in the 4 capital cities in Australia and in New Zealand earlier this year. We were privileged enough to have Guido Tronca from ProSec backing us up on this event, and we also had the very first chance for people to train and try the new ProSec GPR Live and the Pundit 250 array I mentioned previously. So this was a really exciting event, but the best content from this was talking about the different technologies and its applications. So when we want to scan a concrete structure and find out some of its geometry, how thick it is, how it's laid out, or some of the structural embedments, there's a few different tools we can reach for. There's eddy current, which in particular is the technology used by cover meters. So the Profoscope cover meter is a simple one that just measures cover depth and locks onto location, but if we look at the Profometer cover meter, that is a whole scanning tool that can show the layout of the reinforcing steel. We'll also talk about ground penetrating radar, the most powerful tool for imaging metallic and non-metallic embedments in concrete, and talk a bit about what the ProSec GPR Live is doing that's different. And we'll look at ultrasonic imaging, which is such a powerful tool for defects and air voids. So the key thing to understand about eddy current is it is a shallow technique which finds only reinforcing steel. So you have maybe 120 to 140 mils penetration depending upon the size of the reinforcing in the structure, and it will measure very precisely the cover depth, so cover from the top surface of the concrete to the top of the reinforcing bar. And it is also the only tool that will estimate the diameter of those reinforcing bars. I do stress that it's an estimate, but it is a useful tool to compare covers over the structure. The Profometer in particular is even more precise than that because it has artificial intelligence functions, which ProSec are working heavily to incorporate, which let it adjust for very congested reinforcing regions. Now, ground penetrating radar is an electromagnetic technique, which is very sensitive to metals, but is also sensitive to change in materials. So it can pick up things like the back wall of a structure where that structure is exposed to air. And then finally, there's ultrasonic scanning, which is not so sensitive to steel, but can pick it up if there's enough of it and it's in the right position, but is very sensitive to air. Even something like a fairly narrow delamination is very visible with an ultrasonic pulse echo imaging tool. Now, to talk about why this is, we need to look at what happens when a signal is sent from the surface of the concrete through the material. If we send a sound signal or a radar signal, so we'll start by sending a radar signal. Where it meets a concrete air interface, it reflects a portion of that energy. A lot of the radar energy keeps going past the back of the structure into the substrate, and what that means is we can see that join weakly, but we have the ability to see beyond that point in the structure as well. The things that you see strongest with an imaging technique are also often causing a shadow or a block of what's behind them. So if we use a sound wave to a concrete air interface, we return all of the energy. So we get a really clear image of that break, but we can't see beneath it. Similarly, if we send a radar signal to a steel embedment or a steel plate, it's completely reflected. All the energy comes back to our sensor. And if we send a sound wave to a steel interface, some of the energy will travel through. We don't have as strong an ability to image the steel or see the steel, but we can see beyond it. But if you're choosing a technique and you want to locate steel, I would use a radar system. And if I wanted to locate damage or voiding, I would use an ultrasonic system. So, the generally recommended applications for radar is the location of reinforcing, and It's also very quick. They're a rolling scanning system, so you can pick up a lot of information very quickly. So if you need to survey structures quickly, radar's also a go-to. Now, it's not just for rebar. It's also suitable for post-tensioning location, pre-tension cables, metal plates, non-metallic reinforcing, void formers, anything in the structure that is big enough to return a signal, and that will depend upon the material how big that needs to be. Now, with an ultrasonic tool, it is the most powerful tool to find physical breaks in that concrete substrate. It's the tool you can reach to when there's a lot of congested steel and you need to know what's happening behind it. So if you think there might be something occurring in the middle of a large bulk concrete structure which is heavily reinforced, the only way you're going to get past that external layer of very heavy steel will be with an ultrasonic tool. And finally, eddy currents. Very shallow, but extremely precise. If you're doing a durability survey or a QA survey of cover, the reinforcing cover meter, Profimeter or Profoscope on the ProSec side of things, is the correct tool. Now, the advantages of the GPR is you're going to see the individual rebars very cleanly, and you don't need to bond the sensor onto the surface. So if you have a small air break, like a delaminating surface coating, if you've got to work over a rough surface and have to lay a plank, none of that's going to reduce your GPR's ability to be used. You might need to be a little bit more cautious in what you're doing, but the results are still available. Now, with ultrasonics, you can measure into complex areas, and it's also very sensitive to air. But the cover meters are very precise, and they're the only tool that's going to estimate bar diameters. You're going to see the position of a bar with a radar system, and you may see the position of a bar with an ultrasonic system, but you cannot determine from the data those GPR ultrasonic systems collect the real diameter of the bar. The cover meter's estimating it, but it's able to offer that estimate. Now, the limits is if we put a lot of steel up front of a radar system, we're going to pick up that steel very cleanly, but we're not going to be able to see what's happening underneath it. Also, if we have a subtle delamination, we've had corrosion occur, there's been a little bit of a break at the level of the reinforcing, or a topping is separating slightly from the slab, we can't test for that. We can't determine the extent of that damage. Also, GPR is very affected by moisture level. So if you've got very wet, very young concrete, it's going to limit the penetration. For an ultrasonic system, if you do have that slight delamination, you're going to pick it up really strongly. It's going to be very obvious, but we can't see beyond it. Also, because the arrays need to bond each point onto the concrete with pressure, if you have a very rough finish or a very powdery finish, or you've got the wrong sort of coating on the concrete surface, an ultrasonic test won't be suitable. And the big limitation of the cover meter techniques is they are a shallow test. They're only the first top layer of that reinforcing inside the structure. So the ProSec GPR Live is the latest system from ProSec, and I'm going to take this chance to talk a little bit about how GPR works and what's different with this machine compared to a conventional pulse GPR. So with GPR, we're sending a signal and we are picking up any returning echoes in the structure. That signal's not coming out like a laser beam. It's coming out as a broad energy from the antenna, and we're receiving reflections before and after we enter the structure. This forms a characteristic hyperbola shape in scans as the antenna moves past. I'll show you that working in a second, but we can see in a real scan we've got hyperbolic shapes on what would likely be the reinforcing steel, and we also have a flat, what we'll call be a linear reflection, which is caused by a curved element inside the structure. We might be running over top of a post-tension cable, or a curved back of the slab here. We haven't done enough to determine exactly what that is. We take additional scans to interpret this image. Now, if we want to clarify the exact position of a bar, or make this image clearer for a layman to interpret, we can use what's called migration. Migration takes those hyperbolic hill shapes and it transforms them into points. The way it does that is the machine will collect the hyperbola, the individual signals from which form the hyperbolic shape, and it will mathematically transform them from that curve according to time to their real position in the structure, both vertically and horizontally, locking that bar into a clean image like this. So this is the same structure where it has been migrated. The image is now transforming hyperbolas into single points. It's possible to go beyond this with processing and get what are called time slices or depth slices, where we look at the stack together several scans and create a top-down C-scan is the technical term for this image, which shows the individual reinforcing bars as they exist inside the slab. Now, again, this is just their position, it's not their size. And let's see again here a little bit more clearly the kind of images presented. And it's also possible with the ProSec GPR Live to take that 3D data and produce an isosurface like this, which is a wonderful way to show the real internal elements of the structure. So we've moved to an iPad-based interface for this, which means we have all the benefits of a modern tablet computer. We can take text or audio notes. We can photograph the position of the scan and document what we're doing as we work. The system also saves any processing steps the user makes as he works, and the position, just the location of the scan was taken. So if you're scanning in Auburn today, it'll let you know which one's building A, which one's building B when you get back to the office and are preparing your final reports. So that's the quick overview of the ProSec training event and the most relevant slide. Now there was a lot more that we covered, and if you do have a desire to learn more about how to investigate unknown structures, to look at durability of structures, or the ability to evaluate structural properties like strength using ProSec equipment, any of your local PCTE engineering staff would be very happy to organise some formal training or an informal tech presentation, a bit of an overview depending upon your requirements. I'm now going to go to a quick preview of our content for next year, which is the coating webinar. This is going to look at all kinds of coding investigation tools in an Australian context. I'm going to look at the Australian standards for wet film, dry film coating inspection over steel and over concrete. And I'm going to talk about some of the special techniques and requirements when you are testing complex situations like a coating over a non-metallic substrate or a concrete substrate. And as I said, in a second, we're going to talk about galvanizing, but I'll be repeating that during the webinar as well. I'm also going to look into the other tests you would do on a cured coating, like coating adhesion, and some of the chemical tests needed before you place coatings over steel. So we'll talk about that more generally next year, but for our overview today, I wanted to talk a bit about how galvanizing is measured by a dry film coating thickness machine. The thing to understand about dry film coating thickness machines is they always operate using a magnetic principle. Some of them will use the same principle as a cover meter, which is pulse induction. Others will use a fixed magnetic field. If we use a fixed magnetic field, the only material that field is sensitive to is ferrous metals, so a steel or an iron. And if we instead use a pulse induction, it is now sensitive to non-ferrous metals as well. So if we use a probe that can switch between ferrous and non-ferrous testing, this is how we can evaluate a galvanizing thickness. Because galvanizing is a non-ferrous zinc coating over a ferrous steel. So by measuring the thickness using a ferrous gauge, we ignore the galvanizing and we pick up the steel thickness. The other key thing to understand is when you have a chemical coating like this, there may be a slight inconsistency, a inherent roughness in the material. So it's important to collect a lot of measurements and average the results to get the expected average thickness of that zinc galvanizing. Also, the table I have here in blue is simply the conversion between thickness measurement and the amount of steel applied per meter, square meter. Amount of zinc applied per square meter. And what becomes interesting is we can take advantage of this further to measure a duplex coating. If there is a plastic or a paint coating over the galvanizing, we can determine the overall thickness to the steel using the ferrous gauge, and the thickness through the conventional non-metallic paint thickness using the non-ferrous measurement. And subtracting one from the other gives us our paint thickness. And there was a specific model of Positector by DeFelsco, an FNDS, which will record both measurements automatically. So if you have large volumes of a duplex coating, it's possible to document this very quickly. So that's what we're looking forward to next year. But to complete our discussions of this year, I'm going to go through just a sampling of the two previous webinars. These webinars were presented earlier in the year. The first one is looking at the non-destructive tests that are mentioned in AS5100.8. Now, if you do want to learn more on these topics, all you need to do is stay right on our YouTube channel where you are now, look at our previously recorded videos, and you'll find both of these webinars in their complete version saved as a backup. So there's a lot more to go through here if you want to do some training before you finish up for the year. Now, 5100.8 is the new bridge code. It was released in April of 2017. It covers the design of bridges, and it has specific applications for concrete bridges, steel bridges, timber and composite construction. This is the global bridge code. It's the design of new bridges, but new in 2017 was a section that covered the rehabilitation and strengthening of bridges. And what that means is that now there is a formalized design approach to designing or remediating an existing structure. Sorry, I've just had a quick interruption on the stream. We're back up now. Give me 1 second and I'll go back to the previous section. So, as I was saying, AS5100 was is the new bridge code which covers design of all bridges, new, for concrete, steel, timber and composite construction. A new section in 2017 was the 5100.8, which is the rehabilitation and strengthening of existing bridges. This is important because it's a formal design approach for increasing the load capacity or remediation of existing structures. And because it's a modern standard, it's also holistic. It doesn't just go, if you wish to design a steel plate reinforcing, you do it this way. It covers the investigation, which is used as input to that design. So, as part of that investigation, a number of non-destructive test methods were mentioned. The previous webinar covers the whole breadth of these in quite a bit of detail, but I'm just doing a quick best of here. In particular, I'm going to talk again about cover meters and GPR. And potential mapping, which if you may also know by half cell potential measurement, electrochemical measurements of reinforcing, and impact echo. What I'm going to do for each of these is I'm going to talk about what the standard, which is ASTM 5100.8, defines this test as suitable for working with. We're going to skip over the theory briefly because this is a summary, but the original webinar has that content. And we're going to give it, from what the standard recommends it's used for, I'm going to give a traffic lights category for, is this a really good application of that test technique? Or do you need to have a great deal of knowledge and experience in that technique to work in that particular method? So, looking at cover meters, it mentions that the cover meter may be used to determine the location and orientation of reinforcing steel, measure the depth of concrete cover, and estimate the size of the reinforcing bar, which is correct. That is exactly what a cover meter is used for. It also defines the accuracy which a cover meter should have, which is plus or minus 1 mil at a depth of 25 millimeters. A modern pulse induction cover meter, like a profoscope or a profometer, will have that capability. So, location and orientation, absolutely, this is exactly the right tool. Also, as I was talking about in the previous section, they are the most precise measurement of cover. The bar diameter is an estimate. That's fine, it's useful, but you never want to take a report from a cover meter and write it straight into your final report. And it's okay for coring work, but we're limited by penetration. So if you expect it to be a complex structure with more than a single layer of reinforcing, you may need to access both sides, or you may need to use another scanning technique for coring work. It is ideal for working out regions of insufficient cover, or cover that is equal to the depth of chloride or carbonation when you're doing durability assessment of structures. Current flow refers to using the cover meter to determine spacings between bars during cathodic protection design, and it is a good input for that. The other thing to understand is they are certainly weaker in areas of congested reinforcement. Now, ground penetrating radar, the standard defines it as able to provide information on reinforcement location, size and arrangement, to find other buried steelwork, to measure the concrete cover, look at the thickness of the structure, find pre-stressing strand from cable ducts, determine zones of moisture content, and to look for delamination and honeycombing. Now, we've already discussed in a little bit of detail where GPR is ideal for the applications and where it's a little weaker, but I'll reiterate again. GPR absolutely is good for reinforcement location and arrangement. It does not give us size. The size should not have been in there. There's approaches that can estimate the difference between a very large element, like a post-tensioning strand, and a reinforcing bar, but you're not going to be able to tell if it's a 60 mil or a 20 mil bar using a radar system. It will find buried steel very well with the ProSec GPR Live, maybe as deep as 700 mils. It's also suitable where you have a suspended slab, or the element measured has air as the back of it. You can determine the thickness up to, again, the limits of the machine. For the ProSec GPR, about 700 mils, which is great depth penetration. But once we come to delamination, honeycombing, cracking and voiding, it needs to be substantial. This is not something where you're going to find a fraction of a millimetre separation at the reinforcing layer, or a few points of honeycombing. This needs to be catastrophic levels of damage to be visible on a GPR strand. And moisture. There's a particular approach where you can determine moisture in concrete, but it depends upon a change in the speed the radar moves. It is not as simple as moving the antenna over the surface and looking at a value for moisture. You instead need to scan a very consistent thickness, something like looking at the thickness of the structure and see if it changes. I do not recommend this for moisture testing, but if it's relevant, I'd be happy to discuss the approach in more detail a bit later, today or in person. So do let me know if that's something useful to you, but not a out-of-the-box thing you can do right away. Now, potential mapping, also known as half-cell potential measurement, is a way to map out the likelihood of corrosion over the structure using measurements versus electrical reference cell. A couple of key things in the standard text here. It defines the maximum spacing as 300 millimeters. Your actual choice of spacing should instead be based upon your element. So if you've got fairly shallow cover or fairly low resistivity concrete, a 300 millimeter spacing might be just fine. But if you've got thick cover or very high resistivity concrete, I'd suggest you use a larger spacing. So the key thing to understand with potential mapping it gives us the likelihood of corrosion of steel in concrete structures. In particular, it is very sensitive to chloride-induced pitting corrosion inside concrete structures. If you're looking for the effect of carbonation, or if your concrete structure is completely saturated, so full of water, the half-cell potential measurements are going to be less useful for interpretation. It's an advanced topic there, and you might need to use other tools or a combination of tools. It does not give us any information about the rate that steel is corroding, so how quickly we're losing steel section, nor does it evaluate the actual condition of that steel, how much metal we've lost. That almost always needs to be done by inspection of the concrete structure. Now, corrosion rate measurements, polarization techniques in particular, they're our second tool we can use to evaluate corrosion in structures, and they're the one that gives us that corrosion rate. And that's a different measurement. This is a system that takes what's known as a galvanostatic polarization measurement. A current is applied and it measures the change versus the same half-cell potential measurement while a current's being applied. In particular, the standard mentions polarization techniques. So do take that into account when considering your choice of corrosion rate measurement equipment. The final technique I'll mention quickly is impact echo. Impact echo is a different sonic technique than the one we've discussed previously. It has the same limits as ultrasonic pulse echo, but it's particularly sensitive to delamination. It also has a great deal more depth penetration due to the way it's completed. So if you have bulk foundations, an impact echo test is a very powerful test. I firmly recommend it for use to determine the thickness of the structure and to look for delamination and voiding and honeycombing. But with voids, the voids need to be big enough to show up on the image. And with cracking, it needs to be oriented right. But it's a very powerful tool. You can use it in similar applications to a pulse echo system, but it has certain benefits for larger structures or for speed of testing. But it doesn't have the visualization that a pulse echo system would have. Again, impact echo is specifically mentioned in the standard, but impact echo or UPE are used for similar applications with different relative strengths. So our final section, and again the whole webinar is archived and ready to view, is on the early age strength of concrete. Now, this was a very general topic which I covered a couple of different areas of. In particular, I wanted to compare ways that directly measure a compressive strength, so crushing a cylinder mold test or a core from the structure to determine the in situ strength and what ways can improve that. I also wanted to cover ways of evaluating early age strength without destructive testing, so using a sensor or some other way to determine the strength on site without breaking a sample. In the final webinar, I did summarize the standards. I won't talk too much about the Australian standards or international standards in this one. This is just a quick overview. So the main reasons that we have to learn early age strength is to understand when we can work with that element. Can we take formwork away, or can we apply post-tensioning stress? So to do that, the conventional approach has been to break a cylinder. So cylinders are cured in a normal 23 degrees curing bath as per the Australian standard. After a day, they break the cylinder. If it's achieved strength, everyone's happy. The structure can be now stressed or formwork taken away. The issue with that is the concrete on site is not sitting in a curing tank in the lab. It's instead curing under real conditions where heats may be higher or lower. So that cylinder in the lab is not going to correctly capture the real strength. It may be a safety issue where there's not sufficient strength gained even though the cylinder breaks as safe, or it may be a time issue where the cylinder is breaking under strength and it becomes important to confirm that it's still safe to work to now rather than to lose schedule because of that. So I'll mention as a way to improve cylinder breaks is to use match temperature curing. Now, in situ measurements, we're using it for the same reasons, but now we are forming a correlation to a test mix done in the lab. And Schmidt hammers everyone should be relatively familiar with. There is a ability to use those for early age strength under the right conditions. And maturity measurement is a very powerful tool for on-site or precast applications where you want to use that to supplement or replace early age cylinder breaks. It captures the real strength at the point of the sensor. So match temperature curing is a way to improve our early age cylinders. Rather than place them in a standard 23 degree bath, the bath is a heating or cooling bath linked by sensor into the real structure. So a sensor is placed at areas of critical strength gain, and the bath now follows that. So our cylinders are going to sit there, and they're going to cure under the same heating conditions as the in situ concrete. So when they break, they should break at a strength closer to conventional strength. Now, I mentioned both accelerating and conventional curing here, because once we get beyond a certain heat, you need to treat your cylinder mold like a mold you would use for accelerated curing. It's also important to get the cylinders into that curing environment earlier than the 24 hours on-site curing conditions would be. So they may need additional protection from the water in that bath. They may need to be in a sealed mould, or some other approach where that water cannot affect the concrete in its very early stages of strength. Schmidt hammer testing is an in situ test of surface strength. There is a correlation you can build for the material. Now, if you're using this to measure early age strength for your project, you practically need to use a custom curve. So do your own test mix, test the cylinder samples with the Schmidt hammer, and then break them and build your own relationship. So it's important to do that if you wish to use this to evaluate strengths of that material. And those correlations are specific to the local materials and the local mix. So that you need to conduct sensitivity analysis to work out for what range of strengths and what range of materials that's relevant. Now, concrete maturity, similarly, we're going to correlate a maturity index to a cylinder strength. So we're doing an oversized test mix again, but this time we are using temperature sensors and the time that concrete has existed at that temperature to build a relationship. Now, one of the critical things to understand with maturity, and when you're building a maturity relationship, is we are curing our test batches under standard laboratory curing conditions, 23 degrees C, and we are placing two temperature sensors and logging what's happening to that temperature as those cylinders are cured under normal curing conditions. We are creating a relationship curve, and that curve then matches up to the rate of strength gain. And if we place the same sensor out on site and we record the temperature variations on site, we can do the same calculation backwards and come to the strength gain on site from that lab sample relationship. And so we can pick up if things have cured quicker due to additional heat, or if there's been a slowing down of curing due to cold nights. Now, this relationship is normally used for a compressive strength test, but it's also possible to use it for other things like a flexural strength, provided you cure and break the appropriate samples according to the appropriate standards. There is a relevant American standard, and that standard can be worked through with NATA to be compliant to that standard locally. So the final part I want to show is just a bit of a comparison of the techniques, the ones I mentioned and the ones I haven't, and where those relate. So the early age cylinder test, this is the conventional cylinder in standard curing environment. It's not repeatable in that we can only break that cylinder once. So if we've got two cylinders for early age strength, we break one and we're under strength. It's a bit of a guessing game how long we want to wait to break the second one and what happens if that one's under strength too. So we can't repeat the test. We're limited by how many samples we have. But it is a direct strength test. We are physically breaking concrete and getting the units of MPa directly from our test. It does not take into account the in situ temperature. If we take into account the in situ temperature, we better capture the real strength of that structural concrete element. And the relationship quality is good. It's the same material, curing correctly, but because it's not going to be at the same temperature, it's usually going to come in somewhat lower or somewhat, or again, if we have very cold conditions, which are less common in Australia, somewhat higher than the strength. But there's no additional setup requirement. It's already the standard procedure used here. Now, co-locations of cylinders refers to placing cylinders with the concrete that's curing. This is more common with something like a steam curing environment where the cylinders are placed inside the steam curer, or in a water curing environment where the cylinders can be placed inside a water tank next to the water lines. Again, it's a direct strength test. The relationship, depending upon how where those cylinders are placed and how good a model that is, can be quite a good relationship, but it'll vary. And it's, again, fairly straightforward to do. Now, match temperature curing, you do need additional equipment, but you have a direct strength measurement, so we go straight from test to MPa, and you've got a nice relationship of the in situ concrete strength to the sample concrete strength. Now, if we take one of our correlated methods, we no longer have a direct strength relationship. We're instead relying upon laboratory work to correlate on site. What this practically means is we need to be cautious and make sure we're confirming the relationship's validity during the setup stage and during the run of that project as well. If we are using maturity, we're capturing the in situ temperature. We don't capture that with the penetrometer or Schmidt hammer testing. And the relationship quality, maturity is very good. The Schmidt hammer is okay if you use a custom curve, but the manufacturer curve is not really a technique you'd want to use. The key thing here is there is a setup required, but not very much equipment. It's fairly straightforward once you've got your test mixes done to roll this out over a large-scale project. So, well, thank you so much for joining us for our overview webinar. I hope that was a good finish to the year for you. And we're going to be having a little break over Christmas. Most of the offices will be closed by the 23rd of December. And but our phone lines are going to be available at any time. So if you have an urgent requirement for equipment, or if you need some direct support over this season, you're not without support. And in particular, our service centre is still going to be open for most of the break. So if you have equipment that needs calibration or repair over the break, and it's a good time where things are stood down to send that in, please do. You can email support@pcte.com.au to organise that. And we'd be very happy to help out that calibration while you're away on holiday. Other than that, Merry Christmas. Thank you so much for joining me. Does anyone have any more questions or anything else they'd like me to cover while I'm live and available? I'd be very happy to discuss anything from the webinar or outside that before we finish up. I'm just watching the live chat now. I've got a little bit of a delay on my side, so I need to wait for anything to appear. Now, if you've got this full screen, just close the full screen and the live chat's on your right-hand side. Okay, I'm not seeing anything, so thank you very much for joining us. I look forward to doing this again in February of next year. We'll be discussing coating inspection and the Australian standards and international standards that relate to that. And have a lovely end of year. Good afternoon.